Okay, we're in business. Okay, so today, to finish up our discussion of CMOS digital circuit design, I'd like to talk about the design of a type of circuit called a multiplexer. And in particular, we're going to look at a 2-input multiplexer. And what this is a circuit that will have two inputs, let's say A and B, and it will have a single output Y, and it'll have a thing called a selection signal here, S, and what this will do is it will make Y equal to either A or B depending on the selection signal S. So we could describe the behavior of this as something like Y is equal to A if S is equal to, let's say, 1, or it's equal to B if S is equal to 0. And we can write, we're assuming here A and B are Boolean logic inputs here, and so we can write this also in a Boolean equation as Y is equal to A ANDed with S or B ANDed with S bar. And what we would like to do is, at first we're going to synthesize a CMOS circuit that does this. And so our approach is going to be to effectively synthesize a circuit that implements Y bar and put an inverter on the output. Because remember, CMOS is an inverting logic family, and so it's easier to synthesize Y bar and put an inverter on the output. So to figure out how to do this, what we're going to do is invert this whole expression, AS or B S bar, and then we're going to use De Morgan's, one of De Morgan's laws to push this overbar down onto these guys and change the OR to an AND. And so we get AS ANDed with BS like that. And we're going to use De Morgan's other law to push the overbars down one level further. And this is going to be not A or not S, ANDed with not B or not S, like so. And we could take this double overbar here away, but I'm going to leave it there because we're going to use this to synthesize a pull-up network. And if you remember, a directly implementable CMOS pull-up network is made with PMOS transistors, and so we want the literals or the Boolean variables to be complemented to match with the bubble on the gate. And so our pull-up network for Y bar would look something like this. We'd have two things in series, and each of those things will have two transistors in parallel. So we're going to have something like this. And our first one will have maybe the A, the S. Down here we'll have the B and the S bar. And then we will have to synthesize a pull down network that is the dual or the conduction complement of this pull-up network. And so to do that, we're going to have here inverter on the output. So this is Y, this will be Y bar. And so we're going to have two things in parallel. with each other, and those two things will have two transistors in series each, and so the two parallel branches will look something like this. And so let's say this left one will correspond to this uppermost structure nearest to VDD, and we'll have an A and an S, and then this one on the right here will correspond to the lower pair of parallel transistors up here in the pull-up network, so we'll have a B and an S bar, and we're going to have an inverter here to generate S bar from S. And so this is a reasonable CMOS implementation of our two-input multiplexer. And that's not a bad review of some of the stuff we talked about a few segments ago. But I want to talk about a potential alternative implementation of this circuit. I want you to consider with me, could I do something like this? Or why couldn't I do something like this? So I have two MOS transistors. I wire their right-hand sides together, and I call that Y. And I put A in here, and I put B in here, put S in here, I put S bar in here, and of course I have to have my S inverter to generate S bar. So here I have, 8 plus 2 plus 2, so that's 12 transistors in my CMOS implementation versus potential candidate implementation that has 4 transistors in it. So can I do this? Certainly the idea that we can use these devices as switches gated by the selection signal, and if one of these is on, the other one is off. Turning the switch on, we just basically connect A to Y or B to Y. That seems like it might be plausible. The difficulty is going to come in because while NMOS transistors are very good at pulling down, they're not very good at pulling up, which hopefully you figured out in Post-Lab 5 the reason for that. So we would say that that the NMOS transistors pass strong zeros but only weak ones. So if we were to put, let's say, S was equal to 1, S bar would be equal to 0, so this transistor would be on, this transistor would be off. If we were to make A 0, then Y would be a good strong 0. But if we were to make A 1, what we would get here is a weak 1. We would say that Y would be about a threshold voltage below VDD, but as it turns out, that threshold voltage, because of an effect called the body effect, isn't going to be like 4.7, or rather 4.3 if the threshold voltage is like 0.7. It's going to be more like 3.5. And that's really not super good, because that's going to be possibly in the range of 1 if we were to follow this up with, let's say, an inverter or something like that, or a double inverter buffer, so that it would restore the logic levels. But that 3.5 volts on a 5 volt supply is going to mean that that first inversion stage would be probably drawing a fair amount of static current, because both the PMOS and the NMOS transistor are going to be on partially, up in strong inversion. So that's the real problem with this scheme. These are, by the way, called pass transistors. And this style of logic is called pass transistor logic. So how can we fix this? Is there a way that we could use this same idea, but fix the problem that NMOS transistors are not good at passing voltages up near the VDD rail, but they are good at passing voltages down near the ground rail? Well, PMOS transistors are actually quite good at passing voltages up near the VDD rail, and they are poor at passing voltages down near the ground rail. So what we can do to fix this is to basically put an NMOS transistor in parallel with a PMOS transistor. Right? So let's suppose we have, actually I'm going to just erase that. Let's suppose we have here an NMOS transistor in parallel with a PMOS transistor. And we put S in the gate of this guy. And we would like this PMOS transistor to turn on at the same time as this NMOS transistor does. So in order to arrange for that, we're going to have to put S bar in down here. And so when S is equal to 1, S bar is equal to 0, this transistor is on, and this transistor is on. So they're both on. And so if A is up near the VDD rail, then the PMOS transistor is able to pass that 1 through in a nice strong way, while the NMOS transistor is basically not able to contribute. But if A is down near ground, then the NMOS transistor is on, and it's able to pass a nice strong 0. And so by having these two transistors types in parallel with each other, working together, when one is able to pass the voltage through, the other one isn't, and vice versa. And so we can complete our two-input multiplexer here by basically just doing the same thing. So here's our other NMOS transistor that's gated by S bar. We have a PMOS transistor here that's gated by S. And so here's B, and here's Y. So here, if we imagine S is equal to 1, these transistors will both be off. And if we imagine that A is a 0, well, A is going to be pulling down Y to 0 through S, through the S NMOS transistor up here. So the A is passed in a nice strong way by the NMOS, and we get a nice strong 0 out, just like before. But if we make A 1, Y will also be a nice strong 1. That'll be mediated through this PMOS transistor here. So this combination of an NMOS and a PMOS transistor in parallel is called a CMOS transmission gate. sometimes called a CMOS switch. And this circuit, by the way, is actually not just a digital multiplexer. This is also a 2-to-1 analog multiplexer, because these transistors, when we turn them on and put them in parallel with each other, are perfectly happy passing any voltage from one rail to the other. And so this is actually a way that people make analog multiplexers, or CMOS switches. Like if you buy a CMOS, you can get a quad 2-to-1 CMOS multiplexer that will pass any voltage within the power supply rails, and this inside is basically how it works. Of course, we have the inverter to generate S bar from S. And so this is actually a really nice implementation of a multiplexer. Very compact, very few transistors. If we're using it as a digital multiplexer, sometimes we might put a double inverter buffer on the outside so that whatever's driving A and B don't have to drive whatever is coming after this. But there's a very efficient way of making things like multiplexers. You can make trees of these things and basically have an 8-to-1 or a 16-to-1 multiplexer fairly easily. You can also make trees of these, but the transistor count here is actually only 6, so it's like half of this one. So I wanted to show that to you, and we'll call that the last little bit of CMOS logic that we do systematically in the class. I wanted to switch gears here and talk a little bit about intrinsic gain. So this was something that you looked at in Lab 5 in the third experiment. So we had intrinsic gain. Of a MOS transistor, and this was basically the product of either GM times RO for a transistor, or GS times RO. So this is the transconductance gain of the transistor times its incremental output resistance, and this is the incremental source conductance times its incremental output resistance. And these are both related to each other because GM is equal to kappa times GS at all current levels. And so we have that basically the GM RO intrinsic gain is equal to kappa times the GS RO intrinsic gain. So if we know that kappa is a number that's on the order of unity, it's like 0.7, 0.8, something like that, 0.6, and we know something about GSRO, we also know something about GMRO, or vice versa. Okay? So we'll often be interested in making approximations based on the idea that GS RO is much bigger than 1, or GM RO is much bigger than 1. And so I want to try to get a handle on this. You were asked to make some plots of this in experiment 3 on Lab 5 for the simulation models of the ALD 1106 and 1107. But I wanted to show you some actual measured data that I took and some plots that I made from an ALD 1107, just to show you kind of how this might look with some real data. But before we do that, I want to talk a little bit about sort of our simple theory for these things. So from the MOS transistor handout, we had, I'm going to focus on the GSRO intrinsic gain. So GS on the EKV model is basically the square root of I sat times SIS, specific current, divided by UT times 1 minus e to the minus square root of I sat over SIS. That's the general expression from the EKV model for the source conductance. And in the weak and strong inversion limits, this boils down to I sat over UT for weak inversion, which means that basically I sat is much less than SIS, like an order of magnitude less, let's say. And in strong inversion, what we get is that the transconductance gain, or the incremental source conductance, goes like the square root of I sat times SIS over UT. And this is in strong inversion for I sat, let's say more than an order of magnitude bigger than SIS. Yep. And RO, our model for RO at all current levels, is some early voltage VA over I sat. And so we can take the product of GS times RO pretty easily here and find that this is equal to on the general GS model will be VA over UT. Let's get the VA from RO and the 1 over UT from GS times, well, we get the square root of I sat upstairs, and we've got a 1 over I sat downstairs. We're going to get the square root of SIS over I sat out front times this factor 1 minus e to the minus square root of I sat over SIS. And the weak and strong inversion asymptotic limits will be, well, if we take the weak inversion limit for GS and multiply it by RO, the I sats cancel. And so we just get VA over UT in weak inversion. And we get basically VA over UT times effectively this prefactor, square root of SIS over I sat in strong inversion. Much greater than SIS. And so we have here an interesting situation. So if VA was a number that was like on the order of, let's say, 25 volts, and UT is 25 millivolts at 300 Kelvin, then this VA over UT would be something like 1,000, give or take. That's roughly 60 dBs in expressed in decibels. And in strong inversion, we have that same prefactor here, say a factor of 1,000 or something, but it falls inversely with the square root of I sat. So the further above threshold we go, the less the intrinsic gain of the transistor is. And that's primarily a reflection of the fact that the The drain characteristic is kind of stretching out this way. VDS sat is getting larger the further above threshold you go. And so the slope deep in the ohmic region for a given current level is getting less and less. And it turns out that quantitatively it falls off inversely with the square root of the saturation current. So if you're 10 times above, or if you're, let's say, 100 times above the threshold current, SIS, then you have basically 1/10, you're down by 1/10 of the intrinsic gain that you have in weak inversion. And now in this theory, the intrinsic gain should be a maximum down in weak inversion. So I'm going to show you some measured data. A few days or a few classes back, we had this. Let's see if I can find it. Let's see. I should have had it queued up. Let's see. Class handouts would have been this one. So this was a set of slides that I showed you guys from a talk that I gave, and I wanted to go back and look at this one. So this is a family of drain characteristics, and I believe I have 10 of them here that go from saturation current down at the high end of weak inversion, and then these are basically kind of in moderate inversion here, and then these up here are in strong inversion. You can see the saturation voltage is kind of starting to increase. This is plotted on a log scale so we can see all of these different characteristics over the vastly different current scales. And so what I did was I took these drain characteristics, which I had lying around, and I did the same thing that I asked you to do in Lab 5. I basically fit a straight line to the initial part here, deep in the ohmic region, fit a straight line up here to the saturation part of the characteristic, and extracted the slopes, and from those slopes I got the GSRO product. And also the early voltage, and then from the current axis intercept, that's what I called the saturation current. And what I want to do is show you a couple of plots that I made, and I'll put these up on the course website. So this first one is a plot of early voltage as a function, early voltage as a function of saturation current level. And is that control going to disappear? No. Slideshow. Pause. All right, well, this is saturation current on the horizontal axis here, and I have early voltage on the vertical axis. And our typical notion is that early voltage is a constant as a function of current. And you can see up here, up in, say, strong inversion, it's not changing by too much as we change the current by, let's say, a factor of 200 or something like that. It's changing from like 60, like some 58 to 60 or something like that. But down here in weak inversion, it's actually increasing. So the idea that the early voltage is a constant regardless of the current level isn't quite right. I think I might have mentioned, tongue-in-cheek, something called the late effect, which was something that one of my colleagues in grad school sort of named this effect that there's a general sort of increase in early voltage as you increase level of inversion. It's especially true from weak inversion into moderate inversion. And so this simple theory that we had for the intrinsic gain is needs a little bit of modification, because the early voltage is kind of increasing as the source conductances kind of per unit current is at its maximum. And then above threshold, the source conductance starts going down as a function of current. And so when you multiply GS times RO, what you're going to find is that there's kind of a peak in moderate inversion. And so that's what we see in this plot. I'm plotting here the GS-RO intrinsic gain in decibels as a function of saturation current level here. And you can see that we have here a gain around 60 dBs, which is about 1,000. So it peaks up here just about at threshold, a bit above 60 dBs. So 63 dBs would be like 1,400 or something like that. And so maybe it's like peaking at 1,200. And down in weak inversion here, we're down by a few decibels. So, 60 dBs here, and this is maybe like 50, 57 dBs. That's down by a factor of root 2. So it's like 0.707, so this is probably about 700. And then you can see that as we go into strong inversion, we just start decreasing monotonically. And by the time we're up here at the highest current level, which is like 3 milliamps, we're down at about 35 dBs. 30 dBs is about a factor of 30. And so 35 dBs is going to be like a intrinsic gain of like 60 or something like that. Maybe 50 to 60, something in that range. One thing that's interesting to note here is that the prediction from our simple theory is that the intrinsic gain should fall off as the square root of the current. So it falls off inversely with the square root of the current. And so we have here a log-log scale. And so here's a factor of 10 change in current from, let's say, 100 microamps up to 1 milliamp. And we can see here pretty clearly that these 2 points are almost precisely 2 grid spacings here apart, which is a change in gain by 10 dBs, which is half a decade for a 1 decade change in current. So that's exactly kind of a inverse square root relationship. So that theory is actually quite good, and that's pretty much because by the time we're up here, we're sort of in a region where the early voltage is more or less constant, and the model that we have for this source conductance changing inversely with the square root of the current is actually a pretty good model. And so the net effect is that this fall off of intrinsic gain with saturation current follows the simple theory quite well. So this just gives you an idea for typical numbers for these kinds of things. So 40 dBs here is a factor of 100. Okay, so over pretty much most of the current range here, like 4 decades of current, from 100 nanoamps and actually below up to a milliamp, these transistors have an intrinsic gain that's above 100, let's say. And so the idea that GSRO is much bigger than 1 is something that, is kind of a 1% approximation, or sometimes a 0.1% approximation. If we're around moderate inversion, it's going to be more like a 0.1% approximation. And so that's pretty good. That's not bad. Even if we get up here to very high currents in strong inversion, it's still not terrible. So it's still better than a 10% approximation to assume GSRO is much bigger than 1. So I don't have the plots for PMOS. It would take me a while to get the data. I figured it'd be just good enough to show you data from an NMOS and just to give you some idea of what that looks like. Okay, so I think that's all we're going to do for the time being, and we'll see you in class.